the presentation will focus on a mode matching model for slotted circular waveguide antenna. So, go on.
Thank you. Hello everybody, and thank you for attending. My presentation is going to be about a mode matching model for a slotted circular waveguide antenna. And I'm a communication networking engineer. And this presentation is a part of my final year project for BE. I'm going to present it, and it was supervised by Dr. Ali Hamouche and reviewed by Dr. Wahid Kamedi, Dr. Mustafa Ziyadi, and Dr. Ahmed Rafi. Abstract. Slotted waveguide antennas are known to combine high power, high gain, and power capabilities with low cost and size. This design tackles many degrees of freedom that we're going to use to achieve excellent return loss in the CRS band 2 to 4 GHz, as well as gain and directivity. So basically, it was a circular waveguide with slots. I'm going to use different techniques to match our antenna. Antenna specifications. These are the objectives of our design. A reflection loss lower than minus 10 dB. It is well known that the return loss must be lower than minus 10 dB so that it is matched. Bandwidth 10 MHz. It is narrow band. High efficiency, smaller than 1.2 meters in height, so that it can be easily implemented at any site. And cost meet local fabrication standards according to Lebanon. So the most important part of our antenna are the slots. A differential wave slot is simply a cut into a metallic wall that interrupts the current into the current of the waveguide on the outside of the waveguide. It forces the current to travel around the slot and reduce the electric field, and radiation occurs. So it acts simply like a battery, positive and negative. And it is opposite to the electrical dipole. It is a magnetic dipole where the electric field and the magnetic fields interchange. Optimization. So our study is going to be focused on the degrees of freedom that is provided by our antenna. So there are known degrees of freedom that we can use for our antenna. But since the basic of our project of this paper is a circular waveguide, so we have additional degrees of freedom related to the cylinder. The degrees of freedom that we are going to use are the rotation of the end wall with respect to that slot, the end of the cylinder. We're going to move it, the length and the width of the slot, and the length of the probe, the excitation. We're going to vary it so you can see the study. Okay, so the first degree of freedom that we studied is the end wall effect. This is the end wall. So practically speaking, the end wall is spaced quarter lambda g from the last slot, so that the reflected wave will be in phase with other waves after they are reflected. Here is the graph where we studied. We use the end wall as a piston, and we start varying forward and backward to see the best position for the best return loss. As you can see here, this is the practical position used, quarter lambda g, and we vary it backward to become 0.225 lambda g, and we increase the location of the piston until we reach the most optimized location. The most optimized location was found to be at the 0.365 lambda g. We got a almost minus 8 dB loss, which is not enough because we are seeking for minus 10 dB as a return loss. So instead of having a quarter lambda g, we moved the rotation of the end wall to become 0.365 lambda g, and the output was a minus 8 dB instead of minus 1. We have minus 8. So that's the first optimization. The second degree of freedom we use is the width of the slot. The width of the slot is, practically speaking, is used to be length over 10% of the length. that's well known that the width of the slot is 10% of its length. So this degree of freedom can be used to optimize the return loss. So we have only just take 2 points. Here where the width is L over 10% of the length, we got a minus 8 dB as shown before, and we decreased the width of the slot until it became, instead of L over 10, L over 30. Amount of 10%, 3.53% of the length. So these are the position on the Smith chart. The impedance load was here and became here with a minus 10 dB return loss. So we achieved the loss that we are seeking for to be lower than minus 10 dB. And it's near to the center of the Smith chart where we have perfect matching. Okay. The last degree of freedom we used was we varied the probe's length, the excitation. Practically speaking, we use a quarter lambda G, quarter lambda 0 for excitation, and we varied it only a little bit. We started to decrease and increase the length of the probe. So here, as you have the practical length, quarter lambda 0, and we decreased it and increased the length. The best length for the probe was found to be at 0.26 instead of 0.25. And we gained, instead of minus 10 dB, minus 33 dB as a return loss, which is perfect matching. Okay, here we have the summary for all the optimizations. The end goal was located to be at 0.365 lambda G, and the slot we chose to be the length over 30, and the length of the probe was 0.26 and the 0 instead of 0.25. Okay, so the study, we first done study, then we were going to use the antenna, so we fabricated it and we designed it. When we deal with fabrication, we have fabrication errors and effects. The source of errors was the slot width. The width of the slot was supposed to be 2.3 millimeter, but look, when we done it manually, it was very hard to have this dimension. So it was, instead of 2.3, it was almost 3.3. So this affected the loss. The second error, we had diameter of the circular waveguide. Instead of being 8, when we encircled it, it became almost 9. The third error was the roundness of the waveguide. We have a copper tablet and we encircle it to become a waveguide. It is not 100% circular, so this will affect the characteristics of our antenna. The effects were inaccuracy in the return loss predictions. Instead of minus 33, we had another return loss that will show after a while, and lower directivity. Okay, now the lab measurements. The measurements were done at the NDU with the help of Dr. Yusuf Tor. Okay, here are we're going to compare between the simulation results and the lab results. Here the simulation results we have after the fabrication, we done another simulation that take into consideration the errors done by fabrication. So at 2.4 GHz, what our desired frequency, we had minus 18 instead of minus 33. After taking into consideration the fabrication errors, and this is the graph from the vector network analyzer, and it's not very clear here. So at the 2.4 GHz, we had minus 17. So you can see if we can compare between the simulation results and the lab results, have only minus 1 dB difference. So the simulation reflected the real results. And here is you can see the Smith chart where the load is here, which is very near from the center of the Smith chart. Here is our antenna, which is connected to the vector network analyzer. What I want to mention here is that I first mentioned that this study, piece matching, is a part of the whole project. Why did I only mention the piece matching part? Because we have a pending patent. The whole project was to design an omnidirectional slotted circular waveguide. So we cannot reveal all the information It's concerning the slots and the radiation pattern. We're only going to talk about the piece matching until we have our patent, and the rest of the study will be published in further conferences. Okay, now we did another second time measurement with a. Here the measurements were done between 2.2 and 2.6 gigahertz, and our study was at 2.4. The second study had a wider band between the 50 megahertz and 3 gigahertz. It is the whole band that is provided by the network analyzer. And we can see here that it's showing that our antenna is an S-band, so it only functions between 2 and 3 gigahertz. And we have 3 dips. It functions at 2.15, 2.44, and 2.85. And we are just in the 2.4. And you can see the Smith chart load, which is with a 57.3 real part and 4 as a imaginary part, which is near from the center of the Smith chart. Okay, the conclusions. The characteristics that are the problems stated in the antenna were described. We came up with a return loss -33 dB, compactness 1.1, and height. The antenna had a height of 1.1, diameter of 8.3. It was easy to implement, and it weighs almost 1.5 kilograms. And we have a patent pending patent. I want to acknowledge Dr. Yusuf Tawut, which helped me twice with the antenna measurements at the NDU, and Dr. Ahmed Saraji for the paper revision. I want to thank all for your listening and attention.
Thank you. Is there any question?
It was a nice work. I had one question concerning the dimensions. You said that it should be as requirements. It should be about 1.2 meters.
Oh yeah.
So you know
right.
that, okay. You work at frequency 2.4 gigahertz.
Yeah.
You know that the frequency is a function of the dimension?
For sure.
Okay. So if I want to work about 3 giga or 4 giga or 1 gigahertz, the dimensions will vary.
Okay.
Then
Sure.
we'll have one is a requirement.
Yes.
Okay.
For sure. But I'm talking about a 2.4 gigahertz operation frequency. 2.4 gigahertz.
You can't consider it a small antenna.
Consider a small time comparing it with the directivity. It was a very directive, but I didn't mention directivity in our.
Unfortunately, you didn't mention it.
Yeah.
You had, because when you change S11 parameters, you may face some problems in directivity.
The whole study was done, but this paper I'm only concentrating on the piece matching. So the activity and the radiation pattern was not. I didn't focus on it in this paper.
But you did study it?
Yeah, but it's. We have a pending patent, so I cannot reveal information about the activity and the radiation pattern.
What about the efficiency?
Efficiency, it was high because it is only made of one material. Conductor is not another material like dielectric, which has so we don't have dielectric loss and the conductor loss. It is efficient. We tested it.
Okay, I hope to see it on. Thank you.
Okay, thank you very much.
Thank you. Maybe just one small question, not covered by your patent or your pending patent. What do you expect an application for this antenna?
Okay. The title was for my project 5B was for wireless internet applications. That's only for point to multi-point radiation pattern. So, like any wireless application, we have to. This has an omnidirectional radiation pattern. We have to place in the center, and that is 363 degrees, so that everybody can have the signal.
So this is the main.
The main goal was.
Target, okay.
Was the omnidirectional radiation pattern with high directivity.
Okay, thank you.
So finally, the error, as you said, maybe for the material fabrication or the material, then only the errors coming not from material.
No. We have
I saw it. It's portable. It's not too big. Your antenna.
Only 1.1.
So it's not so big comparing to others' antenna.
The errors were in the diameter of the circle waveguide and the slots. The slots are supposed to be 2.3 millimeters, very small. So when I took it to the CNC machine, the tablet started to move a little bit. So the slot, instead of being 2.3, it became 3. So we had a loss in the internals. The internals increased.
Okay, thank you.